Emma,
It's
she was
slope is
second.
0.
What?
Slope is 0. It's always
Yeah,
0,
yeah,
so
we're
that
very-
never changes.
Yeah, average rate of change is zero.
Yeah, I guess. Yeah, I guess. So okay, so she says the rate of change is 0. So if the rate of change of a function is 0, then it's just kind of not changing, right? So if a function which is not changing, then it must be constant. That's actually great. Great, perfect answer. I love it. Anyone else? Someone else almost said. You sort of said something. It was almost exactly the same thing.
Yeah, the instantaneous change is always 0 for all x.
Yeah, the instantaneous change is always 0.
And like that's kind of constant means that. Constant means not changing.
Yeah. Okay. Yeah. Robbie.
This isn't like super rigorous, but so because f prime of x is always 0, there are no 2 points you can find such that the difference between their y values is not 0.
Yeah, no, I take it back. I think that's very rigorous. In fact, that's exactly what we're going to do right now. Yeah, so let's prove this theorem. So here's a proof of this. Now, I know this is really obvious, but we're going to prove it anyway. It's going to involve the mean value theorem. So proof. So here is my proof of this fact. And I think we're maybe getting better at these proofs. Hopefully we are. So I want to prove if the derivative is 0, then the function's constant. Okay, so let's just let's assume that f prime is 0 on some interval ab, everywhere on some interval ab. I have some function which is 0 on some interval. And my goal is to prove that this function is constant on the interval ab. Alright, well what does it even mean to show that a function is constant? It's kind of a weird, it's a weird thing to try to prove. What does it mean if a function is constant on an interval? Robbie kind of said it, so I'm going to give him the opportunity to sort of talk. What does it mean to sort of break that down, logically speaking, into a lower level statement?
Their value is always the same.
The y value is the same for
Any x value on the interval.
for any x value on the interval. There's a slight rephrasing, yeah?
So if it's changing.
Yeah, but that's not really what it means to be constant. Like, well, the actual definition of constant, yeah, for every x value it's the same, right? Yeah?
Because the rate of change is 0, the y value can't vary from the constant that it's already on.
Yeah, okay, so actually, I think what Riley said 2 minutes ago is actually best, but he forgot it already. Yeah, to show that a function is constant, it's sufficient to show that for any 2 x values on the interval, that the y value is the same. Right? So that is what I'm actually going to attempt to prove. I'm going to attempt to prove that for any 2 y values that they have, for any 2 x values that they have the same y value. And if you kind of imagine the picture, right? Here's A, here's B. What I'm going to do is I'm going to select 2 particular x values from somewhere in this interval, just arbitrarily, x1 and x2. If I can prove to you that x1 and x2 have the same y value, do you guys see how that then implies that all of the y values are the same on the interval? As long as I can show that for any 2 arbitrarily chosen ones. Because, well, first let's just do it. Why is that true? Why must x1 and x2 have the same? So let's do it. So pick any two x1 on the interval AB and x2 on the interval AB. And what I would like to prove about that x1 and x2 is that they have the same y value. Notice, I'm extracting information about the function based on the derivative. What could we do? Yeah.
Mean value theorem?
Apply the mean value theorem. Exactly. Yeah. Apply the mean value theorem to f on the interval x1, x2. You're going to see that this is a formal statement of all the things that you guys have been just saying in words. If we apply the mean value theorem to f on this interval x1, x2, what does the mean value theorem say?
Somewhere.
There exists a point C on the interval x1, x2 such that the derivative at C is f of x1 minus f of x2 over x2, or I guess 2 minus 1, doesn't really matter, but 2 minus 1 over like that, right? That's what the mean value theorem tells me. But of course, what is f prime of C?
0.
It's 0, right? This says that if you take any 2 points whatsoever, their average rate of change must equal the instantaneous rate of change. But the instantaneous range just is 0, right? So I'll just write, but f prime of c is 0 by assumption. So f of x2 minus f of x1 over x2 minus x1 just has to be 0, right? In other words, since the instantaneous rate of change is 0 for the entire interval, then the average rate of change must be 0 over that interval. Because because there's always a point where the instantaneous rate of change equals the average rate of change. But if the instantaneous rate of change is always 0, then the average rate of change must be 0. And of course, if this fraction is 0, what do we conclude?
That the numerator is 0.
That the numerator is 0, and hence f of x1 equals f of x2. So I just picked two arbitrary, it's a very mathy kind of proof, but what I just did was I picked any 2 points whatsoever in that interval, and by applying the mean value theorem on that sort of subinterval, I arrive at the fact that these two are the same, right? And now, Sandeep, I can just repeat this, right? I can pick x1 and x3. And if I pick x1 and x3, well then they must also have the same y value, right? And if I pick x1 and x4, well they must have the same y value. And if I pick x2 and x5, well they must have the same y value. So basically, that sort of proves the fact that I can pick any two whatsoever and get the same y value proves that in fact they're all the same y value, hence they're constant. Cool? Okay.
You should draw the stop sign. Or you showed us how to draw the stop sign at the end of the proof.
What's the stop sign?
Square.
Oh,
Colored in
I
square.
think that's like a Schwartz thing, right? He just does that.
Is it colored in?
Then you're supposed to color it
You
in.
don't have to color it
It's
in
the
that.
stop sign.
It's cool. All right. So one more thing. There's this other concept that came up definitely in this class a couple times. What if you have two functions with the same derivative? Remember this fact?
Oh, yeah.
That if two functions have the same derivative, what can we say about that? Did we talk about this with like?
It could be
They
translated.
could be translated like.
Then they must be, common sense says that if the two functions are changing at the exact same rate at the exact same time, then they're like in synchronized motion, that they must be vertical translations of each other. Okay, we just said that and drew a picture and talked about it. Now I can prove it. How can we prove that this is true? Prove to me that if two functions have the same derivative, then they must differ by a constant.
Wait, didn't we do
We didn't prove it, we just talked about why it's intuitively plausible.
Bless you.
Start out and then do stuff.
So theorem, if this is true, then f is just g plus a constant. We got something to stick to. All right, yeah, it's mean figured out to mean. What do we do?
You make like another function which is just f of x plus 2 of x.
Yeah, same trick. Find a new function which is the difference of those two functions. Now, take the derivative. If we differentiate, we get f prime of x minus g prime of x, and by assumption,
That's 0.
that's 0. Okay, so h prime of x is 0, and now by the theorem that we just proved, if the derivative is 0 of h,
Then h max equals 2.
then h must be a constant function. But if h is a constant function, then, and h, since h is just f of x minus g of x, then f is just g plus a constant. Ta-da. All right, cool. Again, concluding information about the function based on information about the derivative always involves the mean value theorem. All right, awesome. More. Eric, another thing that that differentiation can tell me, and in fact, this is something which I've mentioned it in class a couple times, but it's not something that I ever like stated as a theorem or ever proved or ever expected you to know. But it was something which you sort of discovered intuitively by drawing tangent lines and doing your sketching activity. What's another really, really basic fact about a function that the derivative gives me information about? Too many prepositions in that sentence. What's something that the derivative tells me? Something really kind of common sense.
Slope.
Yeah, it's the slope of the tangent line. Or if the derivative is positive, for example.
Oh, the function is increasing.
Yeah, you guys maybe think this is just kind of obvious. Yeah, if the derivative is positive, that means the slopes of the tangent lines are positive, right? And if the slopes of the tangent lines are positive, doesn't it just kind of feel that the function must be going up? Okay, so yeah, this is true, right? This is a theorem that we were unable to prove until now. So theorem, if a function has we'll just do the negative case. If f prime of x is negative, then f is decreasing. All right. Well, before we can do such a proof, we need to recall the non-calculus definition of decreasing. Because there is a definition for what it means for a function to be decreasing. Rahan, what does it mean if a function decreases? This is another thing you did in that little 2.5-week unit back in October of pre-calc. Yeah, it seems like a million years ago.
For any x greater than, so for given a c, any x greater than c would yield an f of x less than f of c.
Pretty much perfect, right? What does it mean for a function to be decreasing? Go right, move down. I mean, that's basically it, right? If you go right, that's what it means. If a function is decreasing on a particular interval, let's always do it on an interval because, I don't know, just cause. So we're on f is decreasing on the interval AB if and only if it must be the case that for any 2 points whatsoever that I pick on that interval, let's take x1 and x2. So for all x1 on the interval AB and for all x2 on the interval AB, then if you move right, you go down, right? In other words, if x1 is less than x2, then
F of x1 is greater than f of x2.
then f of x1 is greater than f of x2. Alright. This is the formal definition of what it means for a function to be decreasing. If you give me any 2 points whatsoever, the one on the right must have a lower y value than the one on the left. Cool? Okay. And by the way, you can prove that certain functions are decreasing, I don't know, or maybe let's take a function like f of x equals x squared. Suppose, I think this is a really good activity, I do this in functions, but I bet Giles probably doesn't do it. We could prove x squared is increasing on the interval 0 to infinity. It's a little bit boring. How do you prove that? How do you prove that the function is increasing on an interval? Yeah, Emma.
Take an arbitrary x1, x2.
Take an arbitrary x1 and x2. Okay, suppose x1 is less than x2.
And then f of x1.
What do I need to show
That
in order to complete the proof that this function is
f of
increasing?
x1 is less than f of x2.
Yes, because increasing preserves the order, right?
Yeah.
Yeah, so what I need to show is that x1 squared is less than x2 squared.
So
Is
can you just
that true? Yeah, and you just like do some like, probably some like rules of arithmetic need to be used to do that. So let's just call it done. Okay, so the point is, you don't need calculus to prove that a function is increasing. There's a perfectly good, in normal parts of America, they teach this definition in Algebra 2, and then they just probably forgotten and never talked about it again. But this is the formal definition of what it means for a function to be increasing or decreasing. It does not involve any calculus. But now I'm going to get some calculus involved because, so Calvin, for example, like we proved that x squared was increasing because x squared's like pretty easy, right? But like what if you wanted to prove that cosine was like increasing? That sounds like that would be a lot harder, right? But with the power of calculus, it's just a simple matter of knowing something about the derivative. What?
That would be really hard to prove.
Really hard to prove what?
That cosine x is increasing.
Without calculus, yeah.
Isn't it
Sometimes.
not? Oh, in an interval.
On a certain interval, blah, 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 blah. Yeah, I didn't mean always. I meant on a certain
Oh,
interval.
yeah, I was.
Yeah, on a certain interval. So okay, let's do it. So how can we do this? All right, this is another one of those like moments at which I'm going to drag you kicking and screaming with smiles on your faces through a proof, which is not really hard. It's just getting you to get good at writing proofs and stating everything out like logically.
Kicking and screaming with smiles on our faces.
Yeah, exactly. Yeah. So Matteo, let's do it. If the derivative is negative, then the function's decreasing. Do you believe it?
Yeah, sure.
Yeah, all right. So, how should we prove such a thing? Raymond? Laura?
We need to find that x1 is less than x2. If x1 is less, we need to basically
Robbie?
We assume the antecedent of the constant.
Yeah, we assume the end is a trick question. It's the same thing every single time. The theorem is a conditional, so we do the same thing every time. There's only one way to prove a conditional. You assume the antecedent, and it's basically when you assume the antecedent derive the consequent. All right. So we are going to assume that the derivative is negative. And then down here, we will hopefully prove that f is decreasing. Or we'll just conclude, I guess we'll just conclude that f is decreasing. Okay. Laura, now where should we focus our attention? Trying to prove that f is decreasing.
Yeah.
I agree. Okay, how can we prove that f is decreasing? I guess I should do this like on an interval or something, right? Prove f is negative like on the interval a, b. Then f is decreasing on a, b. Okay, well I have this formal definition of what it means to be decreasing, right? It means that.
Definition of a derivative.
What's that?
Can we use like the definition of a derivative and plug those things in or something like that?
Yeah, pretty much. Yeah, pretty much, Matteo. Yeah, Thesis, what should we do now? You raise your hand.
We're going to take an x1 and x2.
Yeah, so we're going to choose arbitrary x1 and x2 from the interval AB. And the picture looks something like this. Here's A, here's B. I'm going to choose, and what should we say about that x1 and x2?
x1 is less than x2.
Let's assume that x1 is less than x2, yeah. We'll assume that x1 is less than x2. Because notice that the statement which forms the definition of decreasing is itself a conditional, right? This is what's kind of hard. This is essentially we're proving a conditional inside a conditional. It's like math. So in order to prove this conditional, we have to again assume the antecedent and derive the consequent. You with me?
Yeah.
So I'm going to assume that x1 is less than x2, and then what's my goal down here?
F of x1 is greater than f of x2.
Exactly. If I can succeed in showing that f of x1 is greater than f of x2 from the assumption that x1 is less than x2, well, then I have completed the proof that it is decreasing. Follow?
Yeah.
And then I would be done with the proof. Okay, so we now make a picture. Here's x1, and here's x2, and x1 is less than x2. So let's just draw it. Well, okay, so now what?
Just draw it.
Draw what, though?
Draw it.
Just draw this so that it looks decreasing?
Yeah.
So why is that true? Why must it look that way?
Because of the condition.
It's like that other problem we did where like we restricted the derivative, like the derivative can only be negative. So like assuming the derivative is like as big as it can be, it has to be like 0 minus. So like if it's like going at 0 minus, then it has to be like a little less than.
Yeah, okay. We have our one thing we're allowed to use, right? The one thing we're allowed to use is that the derivative is negative. What does what relevance does it have that the derivative is negative to me concluding that f of x1 has to be greater than f of x2?
The intermediate value theorem.
Calvin, no, not the intermediate value theorem. Well,
Yeah, I mean, you're saying the definition of derivative, you're subtracting it, the bottom is negative, and the top has to be positive.
Using value.
Mean.
yeah, you use the mean value, right? It's definitely the mean value theorem. It's always the mean value theorem. The mean value theorem is the one thing that enables me to conclude information about the function based on information about the derivative. What does the mean value theorem say? The mean value theorem says on any interval whatsoever, there's some special point which represents the function. Well, what's the instantaneous rate of change of any special point drawn from the interval x1, x2? It has to be negative. So if the instantaneous rate of change has to match the average rate of change somewhere, and the instantaneous rate of change is always negative, then the average rate of change must be negative. That's like the proof in words, right? If we want the proof in math, man, you guys are bored. Then can we just do it, right? So apply the mean value theorem to f on the interval x1, x2. What does the mean value theorem say? It's not really using the definition of the derivative. You know, it's kind of similar. There exists a c.
Derivative s.
F prime c equals f of b.
Well, here I'm.
F of f.
F2. Shouldn't it be on x1 and x2? Not on f of x2 minus f of
Oh,
Yeah.
sorry.
Yeah.
Oh, yeah.
Such that this is this, right?
Yeah.
Yeah. But what do I know about that derivative?
It's less than 0.
It's negative, right? By assumption, here is the crucial point at which I use my assumption that the derivative is negative. Somewhere on the interval, the instantaneous rate of change equals the average rate of change. But I know the instantaneous rate of change is negative, thus I know that the average rate of change is negative. And now, once I have this negative expression, what can I do? I have to do now like an analysis of that fraction.
x2
Yeah.
minus x1.
Multiply the x2 minus x1 and bring it over. And you know the x2 minus x1 is positive because you said x2 has
That's right, that's right.
So
The-
your other assumption.
Yeah, you just look at the denominator. This denominator is positive, right? So if the denominator is positive, but the fraction is negative, then the numerator must be negative, right?
Okay.
So I know that the numerator is negative. Is that okay if I just say that out? I feel like it's okay, right? So that means that f of x2 minus f of x1 must be negative. The derivative is negative, so that fraction is negative. The denominator is positive by my other assumption, was right here. And so I've shown that that numerator must be negative. And if the numerator is negative, just move f of x1 to the other side. Conditional proved, right? Cool? Okay, Howard, do you feel like you could have done this yourself if I just like locked you in a room for 3 hours and gave you like candy bars and juice? Yeah, probably, right? Yeah. It's one of these theorems in which you don't actually have to be smart, really. There are no creative steps. You just have to have enough confidence in your ability to construct a proof to like just to know to like write out the definition and use logic. Are you kind of with me? I don't know. Whatever. All right. Good. That's math. This is amazing. I now can harness the power of the derivative to learn basically almost everything there's to possibly know about a function. And all of a sudden we can do all these things that we could never have done before. So here, watch. I give you a function. F of x equals 3x to the 4th minus 4x cubed minus 12x squared plus 5.
That looks like it.
Please tell me precisely when this function is increasing and when this function is decreasing. Go. Hmm? Oh yeah, how else are you gonna do it? This is not something you knew how to do in pre-calc, right?
Descartes.
You can use Descartes' rule of signs to find out where the roots are.
And then do a
But remember, there was that one thing, you can do a sign chart for the roots, maybe, if you could successfully factor it. But what we never were able to do in pre-calc C until now is figure out like where the relative max is. Right? Do you agree? We never knew how to do that. Remember all the
Extreme.
Hmm?
Is it extreme or extreme?
extrema?
Oh, well.
We could never find those extrema. Exactly. Yeah,
So you
that's
have to
it.
take the derivative.
Yeah. Yeah.
All
That's
we've been doing is taking the derivative.
Yeah, it's
Take the
just,
derivative and
it's just
talk
yeah.
about
Mateo
the
says,
derivative.
dude, do we just take the derivative and make a sign chart? Answer, yes. It's exactly what we do.
Okay. It's okay, I can. What? Oh my gosh, yes, I completely agree. It's terrible outside.
It's just one of those days where you guys feel like you should have had a snow day. It's
Yes.
Like, you just feel like you've been like like the world is like owes you
Yes.
some injustice.
Yeah. Yeah. I was wrong.
No, we don't feel that way. The world actually.
It just is that way. I tried to teach second period this morning. Wow, what a disaster. That might have been one of the worst classes I've ever had. That wasn't my fault.
Give us no
I think.
school.
I like knew what I was talking about. It was like vaguely interesting topic. I was kind of like explaining it well. Everyone was just looking at me like, I hate you. I hate school. I hate life. I don't want to be here. I did not expect to be here today. It was just like the most like morose like environment ever. I was just like, oh god, this is terrible. I would just go work in an office. But
It was very morose.
it was a All right. Did you differentiate correctly? Did I differentiate correctly?
I don't know.
Yeah. I don't know. Yeah, I think I do that. I think that's right. All right. Now this just comes down to, all right, do you have sufficient algebra 2 skills to know precisely when this parabola is positive or negative? And I do. And hopefully you do too, because we did this like a bajillion times. Factor 12x out of all of this crap.
X minus 2, X plus 1.
Oh, she's just doing it for me. I can handle this one. X squared minus x minus 2. And so this is 12x, x minus 2, x plus 1. Is that what you said?
This is
Cool.
algebra 2 skills.
And so I have a function which I've differentiated and I have factored the derivative. And now I can just make a happy sign chart. And the happy sign chart tells me -1, 0, 2. This is cubic, so it's like, what do you want? Boom, 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 boom. So cool. So cool. Now, I can just say for sure that this function is, you tell me. Let's go in chronological order, Gehard.
Well, f is decreasing from -1 to infinity.
Customary to go left to right.
And then it's increasing from -1 to 0.
Yeah, let's keep talking. Right?
And it's decreasing from 0 to 2. And then increasing from 2 to 4.
Bam. Bam, bam, bam.
Wait, so is this?
yeah.
Isn't this kind of like what Mateo just said, though?
Yeah.
What did we say?
Yeah.
He told me to.
Yeah, exactly what Mateo said. And I was like, yeah, you're right.
Oh.
Yes.
Do that thing where you do like f is decreasing on -infinity and -1 union.
No, don't do that because it's actually technically then not correct, right? Because if you're saying that there's like a set, it's like a weird, don't listen to this. This is like a weird thing that says like, because the technical definition of decreasing is if you take any 2 points whatsoever,
Oh, so you could have like the points that are like
right?
across each
But
other.
if you pick points on separate, so don't do it, just say, you just have to write it twice. You can put commas, but don't say unit, because it's not, that set itself is not a decreasing
Have like
set.
one.
All right, so anyone else have a comment to make, seeing as how the theme of this week is finding extrema? Does this new information that I have just gathered about this function, does that seem to shed some light on extrema finding? Yeah, this table.
Well, oh, wait.
Just say yes.
Yes.
Yeah, it does. Yes, Sydney.
Look for like mins and like the parts that
Yeah, but okay, look, I just did a bunch of stuff, right? I now know, so like, is it just, now can I just conclude that, what seems to make sense that I can conclude right now? Yeah, Raymond.
When it changes signs, there's no show.
Yeah, when the derivative changes sign, it seems like there must be, that's all, right?
That's just when the derivative equals 0.
No,
Just
because
when-
sometimes the zero thing was zero doesn't change sign. Like-
Okay, right, so each of these are critical values, right? But what we learned 2 classes ago is it's not sufficient if the derivative is 0 that there is necessarily a relative max or relative min. But here, do you sort of feel that it must be the case that if at -1 I was decreasing and the derivative is 0 and then I begin increasing, that must be a relative min, right?
Yes.
Yeah, and at 0, I don't know where we are to, I guess I do know, we're at 5. At 0, the derivative is 0, and it was increasing up to 0 and is now decreasing. So this determining when a function is increasing and decreasing is also really relevant to determining where the relative maximum and min are. Yes?
Okay, so, wait, how is this different from what we've been doing? Is this just like a proof that
Nah, it's all math, man.
right?
It's all life. What? Yeah.
It's like a proof that everything that we've been doing.
This is a proof that all the crap that Yob has been thinking has been correct all along. Yes, we have kind of been assuming that when the derivative is negative, the function is decreasing, but we've been assuming it in some sort of intuitive, curve sketching-y kind of, it feels like the thingies are kind of going down, and so I feel like it's decreasing, but this is just proof of that fact, right? Yeah, that's all.
It's like because of common sense.
Can I just keep going? What's your question?
Yeah, when it's like, when there's like, you can also put something on the sign chart when it's like going to negative.
Okay, sure. Okay, so, all right, there is a classic, what word am I trying to say? Theorem. The theorem is called the first derivative test. Even though it's called a test, it's just a theorem. But it's a theorem that you like apply so often that you sort of think of it as like a test. All right. And what does the first derivative test say? It just says this same thing that we were just talking about over here. So here, probably have to add some things like f is continuous on some interval AB. F is differentiable on AB, but maybe not at C. Maybe not at C. All right, what's C? C is some critical point. So let C be a critical point. Let C be a critical point or critical value for the function f on the interval AB. In other words, C is just some point where the derivative is 0 or does not exist. All right. So this theorem is like just the most straightforward thing in the entire world. Here's what the theorem says. It says, if the derivative is negative on the interval AC, and the derivative